Hello everyone and welcome to mathematics tutorial number 2 as part of the SE 4030 Key Skills for Chemists module. This is the first tutorial of a short series on algebra, and there are several things that I would like to go over today. Most of this I imagine will be familiar from GCSE mathematics, and indeed will be a bit of a top-up, if you like, a bit of a refresher, a reminder of the kinds of manipulations that we can do in equations in order to simplify them, or perhaps rearrange to get the subject of an equation that we require for a particular calculation. By the end of this session, I would like you to be familiar with several things, and I'll remind you that the learning objectives here will be achieved if you use this short tutorial in conjunction with the resources that I provide in the Mathematics Tutorial 2 section on the Moodle site. So that is the relevant chapter for the Monk and Monroe Maths for Chemistry textbook, as well as the collection of YouTube videos that I apply on the Moodle site. So our learning objectives are to be able to identify and use common operators encountered in chemistry. Some of these are simple, some of these are a little bit more complicated. To be able to use the BODMAS scheme to correctly perform a calculation. Again, this is probably familiar from early studies in mathematics, but we're going to go over it again today. To simplify equations through collecting like terms, to simplify equations through balancing, to simplify equations through cancelling, and finally to rearrange simple equations. Okay, so symbols are used in mathematics, and these are essentially a way of writing things in shorthand. These symbols tell us to do something. All mathematical expressions contain these operators or symbols, and we use mathematical operators to save space and time. So there are some common operators that we use in chemistry. Some of them you're obviously very familiar with, some of them you may not be. This is an example here of the delta operator, and that delta x there, the delta in front of the x, tells us to subtract the initial value from the final value, so it's a difference. There is the sigma operator, which tells us to add up the terms of a series of numbers. And there is the pi operator, which is similar to the sigma operator, but tells us to multiply together a series of terms. So we can look at a worked example here, and this example will show us how to calculate the molecular mass, or the mass per mole, of this ozone depleting compound fluorochloroiodomethane. So there's one of these sigma operators, and I'm just going to talk about its arrangement. So you see the 5 on the top of that sigma operator. That tells us there are 5 numbers in a particular series. Well, in this case, this molecule has 5 atoms. So we stick 5 on the top of the sigma operator. The relative masses of those atoms are shown there, 1, 12, 19, 35.5, and 127. And the overall mass is given by the addition of these numbers. That I equals 1 at the bottom there tells us the lowest number in the series. So when you add those up, you get 194.5 grams per mole. Now, this is a pretty simple example, and in fact, we probably wouldn't use a sigma operator to very simply add 5 numbers in a series. We just write it on a piece of paper or type it into a calculator. But there are some more examples of slightly more complicated molecules where we might wish to use one of these sigma operators. Apologies. we take the number of atoms of type I and we multiply that by the mass per atom of type I. So you see to the right of my sigma operator in this worked example there, the very bottom line, I've got 5 times 12. Well, that corresponds to the number of carbon atoms in my molecule, and it corresponds to the mass per atom of carbon. And you see when you calculate that, you get 115 grams per mole. So let's have a think about the pi operator now, where we multiply a series of numbers together. And this worked example corresponds to a chemist that synthesizes a compound in 3 synthetic steps. Each of these steps has an associated yield. But we need to know the overall yield of the synthetic procedure. And this is really important when you come to perform multi-step synthetic procedures. And you'll do a number of these as you progress throughout your course here. You actually start to do a number of these in this particular module when we do a couple of multi-step inorganic synthetic procedures. So we can calculate the overall yield then as a pi product. And you'll see here what I've done is very simply multiply this series of numbers together. I've got a yield of step 1 of 66%, a yield of step 2 of 92%, and a yield of step 3 as 41%. And I can multiply those 3 numbers together using a pi operator. Now, the previous example I showed you was quite simple for our pi operator, so let's consider something a little bit more complicated, and let's see if we can delve into each part of the pi operator. I've got a series of numbers here, multiplied together, 1 by 4 by 9 by 16 by 25 by 36. And what you'll notice then is that here are a series of square numbers, right, that range from 1 squared through to 6 squared, and we can represent these as a pi operator. So that is that series of numbers represented as a pi operator, and let's have a look at what each individual part means. The 6 on the top corresponds to the highest value of I in the series. So here it's 6, or 6 squared as the numbers are written there. The lowest value of I in the series is 1. So we start with that. We write I equals 1. And finally, the variable I, in this case, has been squared. So we write I squared against our pi operator. Now, there are a number of operators that are commonly encountered in chemistry, right? Some of them are very, very simple. Some of them are a little bit more complicated. So have a look through that table, have a read through the relevant chapter in the Monk and Monroe textbook, and familiarize yourself with these. Things like logarithms and cosines and sines, we will come across these as we go throughout these mathematics tutorials. Okay, so pause for self-test 1 there. Have a go at these. There are 2 sections to this self-test. The first involves the sigma operators, and the next involves the calculations of these pi products. Have a go at them, pause the video, and the answers will be on the next slide. Again, for support, check out the relevant chapter in the Monk and Monroe textbook. And there are the answers to self-test 1. So I want to move on now and consider, if we have an equation, or if we must perform a calculation, what is the correct order to perform that particular calculation in? And of course, it comes back to this idea of BODMAS. If we have a calculation, an equation that we put numbers into, and we as chemists want to calculate something from, then it may have a number of different operators. There might be a multiplication in there might be an addition, a subtraction, a division. And the answer that we get will be dependent on the order in which we perform those operators or in which we use those operators. If we have something with a division and a multiplication in, I will likely get a different answer dependent on whether I perform the division and then the multiplication, or the multiplication and then the division. So we need a scheme to tell us, a set of rules or a framework to tell us the order in which we need to perform these calculations and use these operators. So BODMAS is a really simple way of doing this. I mean, I can remember being taught the BODMAS scheme probably in primary school. So it tells you how important it is that it's taught right from very young ages, right up until sort of university chemistry level maths. And it's important that we refresh our memories here. So there's the BODMAS scheme. I'm sure you all remember that it's a priority system, and it stands for brackets of division, multiplication, addition, and subtraction. And the word of here implies that this involves slightly more complicated operators. So here we're talking about powers and roots and that kind of thing. And the highest priority is given to any brackets during a calculation, and we go right to the other end and look at the lowest priority, which is given to subtraction in any particular calculation. So let's have a look at a worked example. We can express the heat capacity C of a substance in terms of this power series here. C equals A plus BT plus CT squared. Here T is the temperature, A, B and C are experimentally determined constants, and C is the thing where the heat capacity that we're trying to calculate. Now, you will come across all of these concepts as you progress throughout your degree. I don't want you to worry at this moment about what heat capacity is or about learning these equations. We're just looking at the equations and we're trying to apply the mathematical principles that we're learning here. So what order should we perform, or what order should we use the operators in this equation in? Well, in the BODMAS scheme then, you'll note that we look and see that we've got a power in there. We've got a square function or a square operator. We've got a multiplication operator, and we've got an addition operator. So the first thing that we do is we remember our BODMAS scheme, and the operator with the highest priority there is the of operator. So the first thing that we would calculate in that equation is the t squared. The operator with the next highest priority is multiplication. So we calculate the BT and CT portions of that equation next. And the final operator is this addition operator. So we add together A plus BT plus CT squared. And only performing the calculation in that order will we get the correct answer. Now, this is something that I often see students putting these equations, putting these calculations into the calculator and just assuming that the calculator is going to get it right. Well, 8 times out of 10, it might get it right. But it's far better to show your workings on a piece of paper and really divide this any equation up into manageable chunks. And there are 2 reasons for that. Number 1 is that you're much more likely to get the right answer if you really think about applying these rules to an equation properly. And number 2 is that if you do get the wrong answer, but you have shown your workings, then you're far more likely to get more marks. If you just write down the number that your calculator spits out, then it's very difficult for us to award you marks for any calculations. So really, something that is really important in chemistry and mathematics in general is that you need to very carefully think and record the ways in which you calculate an answer. And that's true not just of this module, but of all the modules which have a numeric component throughout your degree, particularly the physical chemistry modules. Let's have a look at this next worked example then. This equation describes the frequency at which a bond vibrates, and it relates the force constant with the reduced mass of a vibrating species and the speed of light. And if we know the speed of light, the fourth constant, and the reduced mass, then we can calculate the frequency at which a particular bond vibrates. But of course, we're interested in performing that calculation in the correct order. So let's have a quick look. We would give the highest priority to the brackets there. So we would first calculate 2 pi c. We would then give the next priority to this of operator. So we would calculate the square root of k over mu. Next comes the division there, so we would divide 1 by the bracket 2 pi c. And finally, we would multiply together those two terms to get the correct answer. So have a pause for self-test 2 here. Have a go at those, and the answers will be on the next slide. And there are the answers for self-test 2. The next concept that I want to consider in this tutorial is simplification. How can we simplify equations into more efficient, shorter equations, more manageable equations? Well, the first way we can do that is to collect like terms. So this is perhaps the easiest way of simplifying any equation. By similar terms or like terms, we mean algebraic portions of an equation that have the same form or content. So let's have a look at a worked example here. Collect together the like terms and thereby simplify this expression. We've got x plus 4y plus 6x plus 2y. So we see that we've got x and y, and we've got some numbers in there as well. Well, the first thing we do is collect together the like terms. So 6 and 6x are like terms. And we must remember that there may be an operator in front of each number. So there is a plus operator in front of the 6x there. So we've got to include that. We then add or subtract those terms to simplify the equation. So if you look at the red bubbles there, x plus 6x, because I'm including my operator here, equals 7x, and plus 4y plus 2y equals 6y. So the equation, when we collect the like terms, simplifies down to 7x plus 6y. A slightly more complicated equation here, including some subtraction operators as well as some addition operators. We're going to simplify this again by collecting the like terms. So the first thing we do is collect the like terms. We've got some A terms, and again, I've included the operators here. We've got some B terms, and we've got some numbers as well. When we simplify those, if you look at the red bubbles, 5a minus 2a is equal to 3a. If we look at the blue bubbles, 3b plus 3b minus b is equal to 2b, and the green bubbles, 3 plus 5 is equal to 8. So that equation simplifies down to 3a plus 2b plus 8. Okay, pause for self-test 3 here. Collect together the like terms in these equations and simplify them, and the answers will be on the next slide. And here are the answers for self-test 3. Okay, so we can expand upon this notion of simplification by introducing the concept of balancing an equation. Now, an equation is balanced when the collection of variables and numbers on the left-hand side of the equation equals and has the same value as the collection of variables and numbers on the right-hand side of the equation. But importantly, we can change around, we can play around with the magnitude of these variables on any side of the equation, so the left-hand or the right-hand side of the equation, providing we do exactly the same to the opposite side of the equation. So let's have a look at a worked example here. This is a really simple worked example of how we can balance an equation and manipulate it in order to get the answer we want. So after a reaction, the mass of a recorded product was 10.4 grams. Incorporated into that mass is the mass of the weighing boat, which is 0.3 grams, and indeed the mass of the product. So we are tasked with trying to work out the mass of the product here. So we start with the following equation where m represents the mass. So the total mass is equal to the mass of the product plus the mass of the weighing boat. And we want to isolate m product. We want to know the mass of our product. So what we've got to do is subtract the mass of the weighing boat from both sides. So m total minus the mass of the weighing boat, and we have to do exactly the same to the other side of that equation. So m product plus the mass of the weighing boat minus the mass of the weighing boat. Well, we know that the mass of the weighing boat minus the mass of the weighing boat will be equal to 0. So what we've done there is isolate the mass of our product by subtracting the mass of the weighing boat from both sides, and we get the answer, of course, of 10.1 grams. Now that's a super simple example, but it demonstrates the idea of performing something on one side of the equation, doing exactly the same to the other side in order to rearrange and manipulate an equation to get or isolate the value that we want to calculate. So pause for self-test 4 here. These are very simple transformations or rearrangements by adding or subtracting from both sides of the equation. Now again, these may seem simple, but write them out in your book. Subtract and add from both sides accordingly to obtain or isolate the number or letter that I ask you to isolate. And although again it may seem really simple, write them out in your book. Answers will be on the following slide. And here are the answers for self-test 4. Okay, so simplification by cancelling then. Cancelling is a really powerful way to simplify equations. When we cancel, we are going to look for like terms on the top and bottom of a fraction. Remembering that if those like terms are multiples of each other, they won't cancel completely since some kind of factor must remain. So let's have a look at this equation. Y equals 4CD over 2. Let's simplify that equation. Well, we can start by rewriting this equation by separating the numbers from the algebraic letters, since the numbers are themselves like terms. So we can rewrite that as 4 over 2 multiplied by CD. And the fraction on the left there is 2 into 4, so it has a value of 2. So that we say that the 4 and the 2 cancel. And what you have then is y equals 2CD, and that equation has been simplified. What about this equation then? Y equals 4 over 3D multiplied by 6 over 20. Well, I can rewrite this equation to make it slightly easier. I can swap the numerators here so that I have y equals 6 over 3D times 4 over 20. And that equation very simply is simplified to y equals 2 over d multiplied by 1 over 5. So pause for self-test 5 here. Have a go at these expressions. Have a go at simplifying these expressions, and the answers will be on the next slide. And here are the answers to self-test 5. So continuing we've looked at how to manipulate addition and subtraction operators. Now I want to look at manipulating equations that contain multiplication and division operators. So we can multiply and divide both sides of an equation to manipulate it. Before rearranging, however, we look for the operator that we're trying to rearrange and we perform the reverse operation. So let's have a look at this example. The ideal gas equation, PV equals nRT. This relates pressure and temperature of n moles of gas housed in a volume V. And we call this R term here the gas constant. Again, you'll study this in physical chemistry. So by use of cancelling, obtain an equation in which P is the subject. So we look at that equation and we see that P is currently multiplied by the volume V. So P is multiplied by V. So the operator that performs the opposite function of multiply is divide. So we therefore divide variable PV by P, remembering that we must also do the same to the right-hand side of the equation to obtain a balanced equation. So PV over V equals nRT over V. We can rewrite that as P times V over V equals nRT over V. We know that V over V will be 1, so P times 1 equals nRT over V. And written properly or simplified even further, that equation rearranges to P equals nRT over V. Now you'll note then that we started with V on the top left hand side of that equation and ended with V positioned on the bottom right. And when we start with a fraction here and we rearrange by multiplying or dividing, the variable we move changes from one side of the equation to the other, but it also moves from the top to the bottom or vice versa. So have a look at this. Look what happens when we multiply this equation here, A over B equals C over D by B. What we actually get is A over 1 equals B times C over D. We've essentially there just rearranged to solve for A. Similarly, when we divide, the variable moves from one side of the equation to the other. And look what happens here when we divide both sides by C. It moves from the top right-hand side of that equation down to the bottom left. Okay, let's have a look at another worked example here. N moles of solute are dissolved in a volume V of solvent to make a solution of concentration C. And N, V, and C are related by the equation C equals N over V. By use of cancelling, obtain an equation in which N is the subject. So we note that N has been divided by V, so we need to get rid of the V term, or we need to move the V term over to the other side of the equation. Therefore, we multiply both sides of that equation by V. So CV equals N times V over V. Now we know in that equation, those two V terms will cancel each other out. And finally, we obtain the rearranged equation for N equals CV. Okay, have a go at self-test number 6. There's some rearrangements there, and the answers will be on the following slide. And there are the answers to self-test number 6. Okay, so we've looked at addition, subtraction, multiplication, and division. The last thing that I would like to look at in this tutorial is rearrangements involving simple powers and roots. We rearrange a power by taking the appropriate root. So again, doing the opposite, just like we did with the previous operators. And we rearrange a root by taking the appropriate power. So let's have a look at this worked example. We devise a kinetics experiment to follow the dimerization of the fluorine radical anion, in this case represented by the Roman numeral 6. The rate of dimerization follows the relationship below here. Rate equals K multiplied by the concentration of Vi squared, where K is this so-called rate constant. Rearrange the equation to make the concentration of Vi the subject. Okay, so let's look carefully and see what's happened to the concentration Vi. Let's see what we have to undo, if you like, to unpick to make this the subject of our equation. Well, it's first been squared to yield Vi squared. Within the BODMAS scheme, we must consider the squaring to be a function of. Next, Vi squared was multiplied by K. So to rearrange, we want to invert each step. We want to move that square over to the other side of the equation, and we want to move K over to the other side of the equation. But importantly here, when we rearrange an equation, we've got to consider BODMAS in reverse now, because we're not calculating, we're rearranging. So here, subtraction would take priority and brackets would take the lowest priority. So if we look at BODMAS in reverse, division comes before that of function. So we start by dividing both sides of that equation by K. And of course, we know that on the right-hand side, both of those K terms will cancel each other out. So we're left with rate over K equals Vi squared. Now we remove that squaring, or that square operator, by taking the square root of both sides. So in this case, the square root of rate over K equals the square root of Vi squared. And remember that the square root of a square reverts back to its original function. We essentially cancel out the square there. So the result of that transformation, or that rearrangement, is that the concentration of Vi equals the square root of rate over K. Let's look at a final example then, where we may wish to rearrange a power or root. Sodium chloride crystallizes in a simple cubic structure. Each side of the cube, we call this a unit cell, has a length L. If the unit cell's volume is 1.728 times 10 to the minus 30 meters cubed, calculate the length of each side. Well, first we rewrite the data that we're given here in the form of an equation. And of course, we know that the volume of a unit cell is given by its length cubed. So L cubed equals 1.728 times 10 to the minus 30. So what we want to do is reverse that operation to find L. So we need to take the cube root of both sides. And if we do that, then we cancel out, or we move the cube, if you like, to the other side of the equation. And we are given a length there for one of the sides of the unit cell of sodium chloride as 1.2 times 10 to the minus 10 meters. Okay, so pause for self-test 7 there. There's some simple rearrangements involving roots and powers. Have a go at them, and the answers will be on the next slide. And here are the answers to self-test 7. Okay, so that's all we've got time for today. Please do get in contact if you're struggling with any of the concepts in these maths tutorials. There are additional videos within this section of Moodle, additional YouTube videos. There is also the directed reading in the Monk and Monroe textbook. Thank you very much.